Alright, I think this will be tutorial 4 on the series of tutorials on hashing, and it's going to be universal hashing. Remember tutorial 3 we discussed simple uniform hashing, so this is tutorial 4. I hope you've been following, and this will really be not too difficult, but I think you need to pay attention carefully as we walk through this because it's a little more challenging than the previous classes we've had on hashing. Okay, if you've not subscribed, remember to click on subscribe button below this video so you get notified when I make new lessons. And also remind you, if you have any challenges, any topic you want to learn, just leave it in the comment box below and I'll get back to you. So what actually is universal hashing? Universal hashing is a better method of hashing. So what does it mean? It says that HK equal to AK plus B mod M plus B. Mod M, mod P, then mod M. So I'm going to just say this is better than the two methods we talked about, division, and we also talk about multiplication. So this is a different method. Alright, this becomes clearer as we move. In this case, we have a and b to be random integers between 0 and p minus 1. K is a key, and p is a prime number that is greater than the universe. So the universe represents the number of hash functions available to choose from. Alright, so let's continue it to become clearer, but just take note of this formula. In universal hashing, the worst case is when k1 is not equal to k2, and then we have probability that k1 equal to that hk1 equal to hk2 is equal to 1 over m. So what are we saying? Let me do a little clarification. So we have that we have a hash table. We have a hash table. No, I can draw straight. So we are saying that we have random numbers. We have k1, we have k2, k3, k4, all the way to kn, right? So we expect that if we hash, let's say k1, it will give us a value, and if we hash k2, it will give us a value. Let's assume we also hash k3, it gives us certain value. Now, if hk1 is equal to hk2, and then that is a probability that is the same probability that hk1, because all of them hashes into a slot with probability of 1 over m. So in the real sense, this probability actually is true, that probability of hk1 is the same as probability of k2. Right, this is the same as 1 over m. But there is something you need to know. We need to prove something about universal hashing. So let me say a few things and then we prove it. We need to choose a function randomly from a set of hash functions. So universal hashing is saying that there is a set of hash functions that you can choose from. So we can call it something like universe of hash functions. Universe of hash functions. So that is the key of universal hashing. There's a universe of hash functions that you need to choose from, okay? It requires H to be universal. So these are hash functions that is taken from a universal hash family or a universe of hash function. And we are saying that the theorem says that for all keys, k is not equal to k prime. We have that hk equal to hk prime, the probability of this happening should be less. Good. So remember, in simple uniform hashing, we say that this probability is equal to 1 over m, right? And we define the load factor to be n over m. But in this case, we want this probability of this happening to be less than 1 over m, or at most 1 over m. In that way, we can have a better hash function. So let's see how it goes. This is the same as saying that probability of h of k1 equal to h of k2 equals 1 over m, as we've said before. So this requires a proof. So let's prove that this is really like this. So the theorem says that for arbitrary distinct keys for random h taken from the universe, then expectation of the number of keys colliding in a slot is less than 1 plus the load factor. So this is the theorem behind universal hashing, and the work that is needed is for us to prove this theory. We need to prove it that the expectation of the number of keys colliding in a slot should be at most 1 plus alpha. So to calculate the expectation of something happening, we need to use something called indicator random variable. What it means is we use indicator random variable to represent these events as they happen. So if we consider keys k1, k2 to kn, we'll say that expectation for number of keys colliding with ki, because now we single out one key, ki, so it will be expectation of iij plus iii. What does this mean? Let's first define what I is all about. I is indicator random variable that is represented by this ij, where j are just indices, is equal to either 0 or 1. So if you don't understand how indicator random variables work, let me know in the comment. Maybe I could make a lesson to clarify. So this event happens, the probability that it happens or expectation is 1. It's only 1 if h of ki is equal to h of kj, right? Good. Where I is not equal to j. So we are talking about collision happening for two k's, ki and kj, that are not the same. All right, so when we have expectation of two keys colliding to be given by I equal to 1, if this is this, so we now sum over all the locations for I not equal to j, for ij, but there will be one collision that will always happen when I. So for the same element hashing into the same place, we have this event occurring must always be 1 when I and I is the same, I and j is the same thing, so it's always 1. So I just hope you understand this. So how we can simplify this is to use linearity of expectation. So what this means is that we can actually sum up individual expectations for each of these events happening. So if we do that, we'll now have a summation of individual expectations plus 1, because I will always be 1. All right, so if we have this for ij has to always be 1, for collision to occur. It cannot be 0. So this is more the same as saying that is the same as saying the probability. The reason is because this 0 doesn't happen because we're only considering when collision occurs. So that gives us the same as probability of Iij equal to 1, right? Good. So the next thing we are going to do is to specify the situation where Iij is equal to 1, and the situation where Iij is equal to 1 is the situation where Hki is equal to Hkj and j is not equal to I, right? And then the probability of this happening is at most 1 over m. By universality, we can sum over all the values of the keys, all the total number of keys, which is n, and that will give us at most n over m plus 1, because we already have 1 in this place. So this becomes the same as, if this is a little confusing, you can pause this video and get your head around it. It's the same as less than 1 plus alpha, because we already defined alpha to be the load factor n over m. So this is what we actually just proved, and this is the universal hashing theorem. So I'll recommend you pause the video and take some time to go through the steps, write them down a few times on a notebook, and it becomes a little clearer to you. So we are going to end the universal hashing at this point. We are going to use it a little later, but for now this is how to prove the theorem. And we are now going to move to universal hash family. How do we determine the universal hash family? And that will be in the next tutorial. I'd like to thank you for viewing. I'd like to thank you for your time and the effort you put in learning. I remain Kyneton the Genius, and I'm your teacher. Feel free to talk to me anytime, and remember to subscribe to my channel, as this will motivate me and encourage me to make more lessons for you.